Now let's talk measures of variation. Same rounding rule as before. Don't round until the end. Use parentheses on calculators or use spreadsheets to help avoid those early rounding errors. And even though I don't have it here, one more decimal place than our data. So round one more decimal place than our data. Some measures of variation that we can talk about. We're going to look at 4 of them: the range, the variance, the standard deviation, and the coefficient of variation. The variance and the standard deviation are very closely related, as you'll see in a moment. And when we talked about the measures of center before, measures of center and measures of variation, we will be analyzing these throughout the rest of the class. So it is important that you understand the mean and that you understand the variance or standard deviation. Those are going to be really important in our future analysis in the class. An unbiased estimator is a sample statistic which targets the value of its corresponding parameter. We use a sample statistic to try to estimate the corresponding parameter. For example, we look at a sample mean to target the population mean. We look at a sample variance to target the population variance. We'll talk about these symbols in just a moment. But we do say that the mean is an unbiased estimator. Breaking that down, here's what it means. If we take lots and lots of samples and we calculate the statistics of those samples, the mean, the median, the mode, the standard deviation, the range, and the variance, certain statistics, the mean and the variance, will center around the true parameter values of the population, while others, the standard deviation, the median, the range, will consistently over or underestimate the parameters. So when we mean unbiased estimator, there are really 2 of them that we'll be focusing on, and a third is the proportion, which we'll talk about a little bit later. Let's start out with the range. The range is just the maximum minus the minimum, the difference between the highest and lowest values in the data set. The variance is the average of the squares of the distance each value is from the mean. We'll have a fancy formula for that, but we will more often than not default to using our spreadsheet programs in Excel or Google Sheets to calculate variance and standard deviation, because they are messy calculations by hand. It is more important that you know how to calculate them using technology and being able to interpret what that number means, as opposed to going through the arithmetic that can become very tedious. Standard deviation, directly related to variance, is the square root of the variance. The standard deviation is a measure of how spread out our data is. So the bigger the standard deviation, the more spread out our data is. Variance and standard deviation are used to determine the spread of the data, consistency of a variable, the number of values that fall within a specified interval in a distribution. This is something called Chebychevs theorem. And they're used in inferential statistics. This is chapter 7 and beyond, to help make decisions. So we'll see those back up for us throughout the semester. Variance and standard deviation, if we're talking about a sample, they have one formula. If we talk about a population, there's a different formula. So it is important to know that there are different formulas depending on if you're calculating a sample versus a population, variance, or standard deviation. Sample variance, we use the symbol S squared to indicate sample variance. We're going to add up the difference between every data value and the mean squared. And once we add those up, we divide by n minus 1. to get the standard deviation sample, we just take the square root. So S is the square root of S squared. In Excel, we have var.s, which will be the sample variance. And for the sample standard deviation, stdev.s. So these are the formulas we're going to be using in Excel to calculate the arithmetic formulas that, again, can get pretty messy. For the population theoretical model, population variance, the big change here is we don't have n minus 1. We have n that we're dividing by. And then notice the symbol. This is a lowercase sigma squared. And then just as before, the population standard deviation is the square root of our variance. It is extremely important that we know whether we're working with a population variance or a sample variance, a population standard deviation, or a sample standard deviation. Most of the times we'll be working with samples. It is really, really hard to be able to collect all of the data values for a population, but we could. One example could be the ages of first inauguration of our US presidents. We can consider that to be a population, and it consists of 45 numbers, so we can create a population variance, a population standard deviation from that population data set. In most cases, though, we're really working with samples. In Excel, similarly, instead of a .s, we use a .p for the population functions. There's an easier way to compute sample variance without talking about the mean itself, and you can see that there's no mean calculation, or there's no mean symbol in this formula. All that's happening is they've done a lot of extensive algebraic rearrangement and come up with a formula so that we do not have to calculate the mean outright. We only need our data values. Just know that that exists. There's another formula you can use. Again, we're going to default to technology. Comparing variations, if we have two samples with the same units of measure, we can compare variances and standard deviations directly. However, if units are different, we need a different calculation. And we're going to look at something called the coefficient of variation. Coefficient of variation is standard deviation divided by the mean, and then change it to a percentage. So this expressed as a percentage, that's why we multiply by 100%. Usually we use the symbol CVAR to indicate coefficient of variations. Because standard deviation is a tough calculation to make, if I have a unimodal distribution that is approximately symmetric, then I can use what's called the range rule of thumb that says I can first calculate the range, divide it by 4, and that will approximate my standard deviation. Generally speaking, we don't want to use this a lot for important calculations. We just want to go ahead and calculate it. But it can simplify if we're in a hurry, if we're doing something to estimate quickly. We can use this range rule of thumb. Next up, we have two rules that we're going to look at as far as indicating how much data we have. First up is what's called chebychevs theorem. The proportion of values from any data set falling within k standard deviations from the mean will be at least 1 minus 1 over k squared, where k is a number greater than 1. And k does not have to be an integer. It can be a decimal number. It just needs to be greater than 1. So what that means is 2 standard deviations away from the mean, 3/4 of the data are going to sit there. So minimum percentage within k standard deviations. This does not matter what kind of distribution we have. If we have our mean given 2 standard deviations away from that mean, 75% of the data is going to sit there. Similarly, for 3 standard deviations, almost 89%, and then 4 standard deviations, almost 94%, 93.75% of the data will be near the mean within 4 standard deviations. And so we are looking at 4 standard deviations from the mean, both directions. It can get a little tricky and a little messy. The thing to notice though is this is for any data set. It does not matter what shape our data set is, but the only way that we can calculate it is if k is greater than 1. So k must be strictly greater than 1, and we can determine the percentage of data values within k standard deviations of our mean. Another rule that we can consider is something called the empirical rule. The empirical rule only works for our normal distribution, which we will talk a lot more about in chapter 6. But for the empirical rule, if I have a normal or a bell-shaped symmetric distribution, percentage of values from a data set falling within k standard deviations is listed in our table. Sometimes this is also called the 68, 95, 99, 7 rule because it indicates these very proportions within k standard deviations. So 1 standard deviation, 2 standard deviations, or 3 standard deviations. If we have a normal distribution, 99.7% of our data will fall within 3 standard deviations of our mean.